thank Anton for the invitation to this wonderful workshop. So it's my great pleasure to be here. So, what I'm going to talk about today is a joint work with Taizawa, in particular the latter part of the talk. So I will talk about, basically I will talk about the mapping. So first of all, let sigma be a compact oriented surface of genus G. Genus G with one boundary component. And I take a base point on the boundary. And let me denote by mapping class group. This is the connected group of connected components of diffeomorphisms of the surface sigma relative to the boundary. So this is the mapping class group. So I will consider a twisted cohomology. So let's V be a left mapping class group module M module. So my basic interest in this talk is will be the twisted, actually only degree 1 twisted first cohomology of N with coefficient E. And actually, there are many important cohomology classes living in such spaces. And just let me show you one example here. So there is a cohomology class denoted by K tilde, which lives in the first homology of N with coefficient strange module. So this is 1/2 of the third exterior power of the first homology of H, the homology of H. So this is called the extended first Johnson homology.
It's 1/2 of 7.
Yeah, I need it. Actually.
No, but what is it? What does it mean? You mean you allow denominators? Do you mean half of the space? What does it mean?
Oh, yeah, think of it as a submodule.
Okay, thanks.
The module is the same as wedge 3 itself. Yeah, if you multiply it.
Yes. Okay. For some reason, I would like to put 1/2. This is for the extended Johnson homomorphism introduced by Morita. And actually, this is very important because by taking some cut product of K tilde and by contracting coefficient by using intersection forms, then we can reconstruct the series of characteristic classes of surface boundaries, so namely MMM classes. So this is the work of Morita. And as I said, K tilde is extended, so there is an original homomorphism called Johnson homomorphism. And actually, this is the series, first in the series of homomorphism called the Johnson homomorphism. So this is the Johnson homomorphism. So, and this K tilde is kind of extension. So as an object, Tau1 is a homomorphism from a three subgroup of the mapping class group to the third exterior power of H. And we can extend Tau1 to a twisted cohomology class of the mapping class group, but to get such an extension, 1/2 is needed here. Anyway, and this is very algebraic object regarding the structure of the trade groups and their subgroups called the Johnson filtration. So this is very algebraic, but I and Nadia Kazumi have studied this Johnson homomorphism from more geometric way by using the Goldman-Leib algebra. Leib algebra. This is Kazumi and myself. Okay. And here there is some formality problem about the algebraic structure of this Leib algebra, and this is where I and Nadia met Anton and Florian. This formality problem is closely related to the so-called Kashiwara-Bain problem. So this is actually an excuse. So sorry, today I'm not going to talk about Grothendieck-Teichmüller group, and I'm not going to talk about Kashiwara-Bain problems, but so it's not so far away. So anyway, I will talk about this twisted homology, and for this. Study is useful to graph on the surface. This is for the structure of path graph complex. So let me give a definition. So let G be an embedded graph in a surface. This is called path graph or ribbon graph. Sign of sigma if the following three conditions are satisfied. The first condition is that this inclusion map is homotopy equivalence. So this is the spine of the surface sigma. And the second condition is that, so this is a definition for once bordered surface. So there is this unique univalent matrix of the graph G, which is at the base point that I chose here. And the third condition is that the other vertices have valency at least 3 for the other vertices. So there are no bivalent vertices. So this is an example of genus 2 surfaces. Yeah. This is an example. Okay. And we collect, so there are so many particle finds. So, and particle complex denoted by G hat. So this is the particle complex. Is a CW complex, which is constructed from all particle spines up to isotopy. So this is a CW complex of dimension maybe 4Z minus 2. And that the two cells are in one-to-one correspondence with a set of particle spines up to isotopy. Particle spines isotopy. And it's the phase relation. Phase relation corresponds to contraction of edges in the particle spine, but the edge should be non-loop, should not be loop. So contraction of non-loop edges. So in this talk, I will consider the first homology only. So it's sufficient to know two skeletons of this cell complex. So let me describe it. So the zero cells of G hat corresponds to trivalent particle spines. I mean, so there is a unique univalent vertex, and the other vertices have valency 3. And one cell corresponds to particle spines where there are trivalent vertices and unique univalent vertex, and there is unique covalent vertex. So this is one cell. So for instance, this is an example of one cell in G hat. There are unique covalent vertex.
The invariant edge is not contracted. The edge connected.
Yes. Yeah. So I should have, yeah. And tail. So this edge is called the tail. So, and then oriented one cells correspond to flips or white-head moods. Among trivalent particle spines. This is why. So this is one cell. So it has a unique covalent vertex, and we can resolve this vertex into two trivalent vertex in two different ways, this and that. So this is one resolution, and this is another resolution. And putting an orientation is equivalent to putting an arrow this direction or this direction. So this is the flip. This corresponds to oriented one set. So, and two cells. Actually, there are two. Trivalent matrix, trivalent plus two covalent matrix, or trivalent. Oh, sorry. Trivalent matrix and one bivalent matrix. And the corresponding shape of the cells to the first case is square, and for the second case, we have the pentagon. And boundary of two cells corresponds to relation among fluids. So we will have a pentagon equation for fluids. Okay. Anyway, so this is the description of the two skeletons of the photograph complex. Actually, this comes from geometry of the topology of the Teichmüller space.
I'm a little confused about the dimension. Is it 4G minus 2? It seems to be too high. Just not enough edges.
Okay. Maybe 40 minus 1.
No.
4G minus 2 is the virtual formula for the dimension of MG, 1.
Okay.
Okay.
Sorry.
So this is the for this version is result. Actually, this complex we have is a dual obtained by taking the dual to some ideal simplicial decomposition of the Teichmüller space. Teichmüller space of C. So this is the space of marked hyperbolic structure on C. And since Teichmüller space is contractible, in particular, this complex is contractible. So it has a natural action of the mapping class group on this complex. So the study of the cohomology of the mapping class group is closely related to the cohomology of the cellular structure of this complex. Okay. Any questions so far?
No, that's just, I mean, I think you're totally right. I mean, if you collapse the graph, right, you have 8 loops and a spine, which means 9, you have a 9-valent vertex.
I think
It's correct. I mean, 9 minus 3 is 6, which is 4g minus 2. It fits. It's all right.
Thank you.
All right.
So now I like to study the twisted cohomology of the mapping cluster by using the cellular structure of G hat. So I like to consider one example. So by the way, maybe what I'm going to tell you now will be very elementary. So I promise. So before that, our interest is in the twisted cohomology of the mapping cluster. And as I said, for instance, the extended fast Johnson homomorphism is an important example. And usually, so there is a cohomology, nice, but it's more difficult to get an explicit cocycle representative for that. For that, maybe one needs to take some choice. For instance, the generators for the fundamental group or etc. And so I will be interested in cocycles of such for the cohomology class. So now let me tell you the constructing some cocycles, starting from cocycles on photograph complex. So let me pick a trivalent photograph spine. Then let me give you the following construction. So there is a map from the space of cocycles of G hat with values in D. So D is an MG module, and taking the class group equivariant part. Invariant part. And the target is the space of one cocycle of N with coefficient B. Here the coefficient is twisted. Then, so this map sends a cocycle C here to CG. And how is it defined?
Is a local system or G hat?
B is just a module, not local system.
Is
That is a spectrum complex. So what does it mean that C is a cocycle here? So recall that the ones oriented one cells are in fixed. So this means that C is a map from the set of free. So this is a set of oriented one cells in G hat to B. And since C is a cellular one chain, so it has to satisfy that C of E dash is minus C of WE, where we have to see that E dash is here. And also it has to satisfy the cocycle condition. So C has to vanish on the boundaries of two cells. So, for instance, it has to vanish on the 5 bits appearing in this pentagon relation. Then now let me give a definition of this cocycle. This map. Now take element in the mapping class group phi. Then consider the graph G that I fixed, and also consider phi Z. This is another trivalent fat graph. So these are two cells in G hat, and since G hat is connected, so we can connect these two cells by a sequence of oriented one cells. So there is this sequence of flips starting from G, and ending at phi Z. Then this map PV sends phi to the summation of the values of the cycle C on WI. So there are choices for such sequence, but since it's C satisfies this boundary condition, it is well defined. In this way, we can we can show that it is a twisted one cocycle. And also actually cohomology class is independent of the choice of V.
So this in the sense that you react on V, like in the cocycle equation, you have the action of the mapping class group on.
Here, yes. So this means that phi, of phi acting on PV side.
And where in C, in the definition of C, does the action of the mapping group happen? Or
Here?
Yeah.
No, here we don't consider. The coefficient is not twisted.
Okay. So yeah, because in your definition of the axioms of C, you don't see anything acting on V. So where is it hidden? Is there any action of
but the mapping is on G. On G. And so I assume that the P is a mapping class equivariant.
Okay, good job. Okay.
Yeah. This is the important condition. Yeah. So let me give you examples. So in what follows, V will be always some tensor module on the first homology group of the type. And I need one notation about the fat graph. So this is a local situation of different spine. And since so for example, let me look at this HA. So since the graph is embedded in sigma as a spine, the complement is a disk. Complement is the disk. So there is a unique homotopy class of simple closed curve, which intersect NA once. So this is A hat. So this is a simple code curve. You are two. Okay. But maybe let me give you another example, which is more visible. So for instance, this is an example of a three-valent particle span. In this example, for instance, if maybe A here, then this is it. And mu A is defined to be the homology class of A hat. So in this way, every edge in the spine gets a homology matching. So this is a homology matching attached to an edge A. Okay. This notation, let me give examples. So first example is used to monitor and tender. So they introduced a cocycle J. The defining formula for it is as follows. J of WE is given by mu A, which mu B, which mu C. So this is in the third exterior power of H. And actually it satisfies the pentagon relation. So it is a cocycle. And we show that the corresponding homology class of the mapping group is equal to 6 times the extended first Johnson homology.
A, B, C are as on the page, as on the board above.
Yeah.
And what makes A, B, and C special as opposed to D?
Yeah.
Why not use A, B, and D?
Yeah, I didn't. But, actually, so there is no, so there are choices. So one could name this edge as A, E, D. Actually, you have to check that this is equal to mu B, C, mu D, mu A. And this holds true because the sum of homology markings of A, B, C, and D is 0. Actually, we have this relation. This we have constructive here. So this is well defined and it satisfies the cycle relation and this equality holds. And actually monitor computes this twisted cohomology and this is rank 2 generated by twice K tilde and some other cohomology. So this is the first example. The second example is simply myself and actually this is much simpler. So we introduced a cocycle called N. This is the mu A plus mu B. And Of course, mu A plus mu C plus mu A, so this is fine. And also we can check that it satisfies the relation. And the corresponding cohomology class is 6 times some cohomology class denoted by K, which is the generator of this cohomology group. This is generated by K. So maybe I should have said here. So here, as I said, it's not so easy to get a cocycle representative on the level of the mapping class group. But this cocycle extends nicely to a cocycle in the first graph complex. And the formula is very simple. And this is the third example. Actually, it appeared in monograph on the decorated Teichmüller scale. The formula is more complicated. So we consider the name of the cocycle difference. And the formula is as follows: mu A, wedge mu B, maybe mu C, times mu B, wedge mu B. So this is the element of the second symmetric power of the second exterior power of H. So the coefficient seems it's strange, but actually this comes from target of the comes from second Johnson homomorphism. And actually, in this case, the homology class lives in the twisted path homology of M with the coefficient. Actually, this homology group is 0, at least over the rationals, and at least in the stable range. So this is trivial.
H2 for this local system is non-trivial stably.
Sorry, which one? This one?
Yes. Can you see it? As, no. Never mind. It's not a question.
And okay. So, okay, in this case, the homology class is trivial, but the natural question would be that if this homology class trivial over the integers, and can one prove it more directly? This is a natural question. Okay, and in the rest of the talk, I'd like to give an answer to this question. So, Sanders cocycle. So, let me look at a trivalent pattern of some particular spine. So there are three edges, and let me name them as A, B, C, counterclockwise way. Okay. And actually, here, this is a very simple observation. So since the sum of homology markings of A, B, and C are trivial, this is trivial, then mu H of mu B is equal to mu B wedge mu C, and also this is equal to mu C wedge mu A. So this element is independent of the choice of how I label the edge. Let me denote this element by eta B. Maybe I should. Now, let me define an invariant of a trivalent particular spine. D is a trivalent, and define psi D to be the sum over all trivalent vertices of G and of this element, eta B tensor eta B. So this is this module. And actually, so this is the answer to that question. So it worked with Takezawa, my former graduate master course student. So I correct psi D for all trivalent particular spines D. So this is a zero cochain. This could be regarded as a zero cochain of the particular complex with coefficient in this module. And also this is mapping class group invariant. This is clear from this construction. And the statement is that this cochain cobounds tenors so that is, if there is a flip from G to G dash, then psi G prime minus psi Z is equal to the value of S. And actually, so yeah, the point is that once I come up with this formula, then it's easy to prove. This is just for direct computation. I mean, I draw this figure of flips, E to G prime, and A, B, C, D, and A prime B, A, B, C, D, and B and G are the same outside this picture. So this difference will be like mu B, which mu P, tensor mu A, and mu G. And the corresponding two terms from the left-hand side. And this is just a direct computation. So anyway, we can have a primitive for this Penner's cotype. And one remark is that so this is mapping class group equivariant cochain covariant case, but here we don't have a uniqueness for such cochain. Uniqueness does not hold. So for me, it was so due to this fact, it was important to come up with the correct formula. But once I found this formula, it is just a simple check. Anyway, let me finish by showing some byproduct of our argument. So from our argument, we can show that the following simple formula. So here on the left hand side, this is omega, is called a symplectic element. So this formula shows some localization formula for the symplectic element. Let me stop here. Thank you for your attention.
Okay, so thank you for the perfect timing. Well, so we have questions. Do we have more questions?
My question is, what is the homology of the fat cross point? It's almost trivial.
Homology.
Yeah.
If you take the quotient by
And you know, kind of the differential preserves boundaries of your fat cross.
excuse me.
The differential preserves number of boundaries of your fat cross. And if you label them, you get an opera. You can compose such things.
I only see this once border case, but I'd like to think about multiple boundary case.
I got a little bit confused about one part. So in the beginning, there was a discussion of one part, but then it never appeared again. So what is its place?
Yeah. So let me try to explain what Morita showed. What this computation of homology. This is the correct group. Here we have Johnson homology. So what does show that the existence of this cohomology class, but so maybe first I should say that this is of rank 2, but twice tilde. So you have to double it to get the integral cohomology class. So yeah, he showed that it extends, but you have to. It's impossible to get the integral lift of tau 1. So I'm not sure if I could answer your question correctly.
Question? Okay, so.